Excellent, excellent. Good evening, everyone. Welcome, welcome. Okay, so people are joining. We're just going to give it another minute or so just to let the last few people in. Who's waiting? Mr. Ibbotson. Still having his Sunday dinner. I think we ought to let him in, I suppose. Right, I think we are about there then in that case. Okay, good evening everyone. I hope you're all well. Hope you've had a good week. Survived the, well, certainly down here in Bedfordshire it was it got very windy over the towards the end of the week. I hope you all survived wherever you were. So we are delighted this week to be joined by Anastasia Kokori. She is the coordinator of the ARIEL ExoClock project and the project manager for the Exoworlds Spies project. So proper scientists, not like us amateurs. Anastasia is going to be giving us a talk about ARIEL and the ExoClock, the future of exoplanets, and how the public can obviously get involved. She's the astrographic officer at Greenwich Royal Observatory and also trained to be a planetary scientist as well at Birkbeck University of London. She's been a graduate of the Space Studies programme from 2018 and also holds an MSc in Science Communications from Dublin City University. We are delighted to have Anastasia with us tonight. So I'm not going to give you a synopsis on the talk. I'm sure you've all read the forum page. Instead, I will just hand straight over to Anastasia. Over to you.
Thank you very much for the kind introduction. Hello, everyone. Many thanks for the invitation. It's a pleasure for me to be with you today, even remotely. Now, I think it has been, everything has been mentioned, so I don't want to say anything about me, but just start sharing some information about ARIEL. The main presentation is focused on ARIEL, which is a future space mission, and then ExoClock, which is a project dedicated to monitor the targets of ARIEL and how ground-based telescopes can help towards this effort. Now, because ARIEL is a future mission, it's very important to start from the current status of exoplanets and share some brief facts about them. The number of exoplanets has been growing fast during the last 20 years, and most planets have been found by the radial velocity method and the transit. And this diagram is very informative to show us that with the red and the green color, we have found most of these planets. And the numbers came mostly from space rather than from the ground. So far, we have found 4,000 planets, and this number is continuing to increase on a daily basis. This is the most recent graph we have here. Of course, we have found different types of planets, and on the graph, again, you can see the planets distributed based on their mass and their period. The color coding is corresponding to the two different methods. The most important, let's say, fact in this diagram is that we have found the gaseous planets, which are on the top of the diagram. And on the right-hand side, on the top part, we have the planets, the gaseous planets, which are much further away, let's say, from the stars. These are the long period gas giants known as the cold Jupiters. So the Jupiter and Saturn are kind of these planets in our solar system. On the left-hand side, we have planets which are gaseous again, but very close to their host stars. And these are known as hot Jupiters. While we move downwards in the diagram, you can see a lot of planets in between, planets that are a bit larger than the Earth, but very close to their stars. These are the warm super Earths, as we call them. And in the bottom, we have planets like the Earth in size, which are the warm Earths, like very close to their stars. The main take-home message from this diagram is that we have only found Jupiter from the solar system analog. So we don't have any other planets. We haven't found any other planets from our solar system around there. So all these types that we have mentioned are something new, let's say. Now, by knowing the mass and the radius of these planets, we can start imagining these worlds by calculating the density and the temperature. But this is quite limited information. We haven't done that for many planets, only for very few of them, tens or less. So by knowing that the planet, for example, we have planets that have very low density, lower than the Earth, but for example, colder and lower temperatures, and these will be ice worlds. So the Barnard star B is one example. Another example is water worlds, where again the density is lower, but because these planets have similar temperature to the Earth, that means that they are made out of water, which is has lower density. K218b is an example. Then we have on the other hand side, planets that are much higher in temperature, and again at the same density, very close to the stars, so their surfaces are melting, and we have some examples of these planets. And finally, we have planets that have extremely high densities, like iron, and in that case, these will be cannonballs. K229b is an example, and you can imagine these planets as bare cores that have lost their mantles and their atmospheres due to the extremely high temperatures. Think of Mercury in our solar system, which is decreasing in size per year, and there are other examples out there. Now, if we take a step back and think of the big number, what we have seen now is like some cases, some small examples of our imagination mostly, because we don't really know what is happening. It's mostly based on some predictions and calculations. The main statistics and what we have learned so far from these 4,000 planets can be, let's say, these 4 points. So first of all, there are at least as many planets as stars in our galaxy. This is a fact. Secondly, most planets in our Milky Way are super Earths, which is a planetary analog we don't have in our solar system. A third point is that there is one potentially habitable Earth-like planet around every M star, and M stars are the red dwarfs. So bear in mind at the same time that the red dwarfs are the majority of the stars in our galaxy. And finally, that 1 out of 10 sun-like stars have one Earth-like planet. And this was the main also goal of Kepler. So this information is what we have so far, not much about their behavior or the nature of these planets. And you may ask how we ended up to this conclusion. So this diagram is shows the distribution of the discoveries, all the discoveries, with regards to the category and also the size of the planets. What is very easy to observe is that we have found around 400 planets like the Earth on the size, and 400 planets like Jupiter, the same number. But because Earth-sized planets are much smaller, they're much more difficult to detect. So in reality, there are even more than Jupiter-sized planets out there. The most interesting fact here is that most planets are in between Earth-sized and Jupiter-sized planets, the super Earth-type planets that we mentioned. So most of them are there. And this is interesting because it's something completely unknown to us, and we don't have much information because we don't have a planet like that in our solar system. There is even a scientific debate about these planets, whether they are larger versions than the Earth or smaller versions than Neptune, so mini Neptunes. And it's something that we don't have much information yet. Now, of course, the discoveries continue. We have a lot of dedicated tools from the ground, but also from space, where the big numbers come. And they will continue to come with TESS, Plato. And so far we managed with these techniques, the radial velocity and the transit method, to find the mass and the radius about the planets. So the information is quite limited, let's say. The mass, what we get it from the radial velocity method. So by seeing the movement of the star, as you see in the graph, we can measure the amplitude, and the amplitude is related to the mass of the planet. So the higher the amplitude, the more massive the planet is. Then we have the radius from the transit method, and the bigger the dip is, as you see in the transit, the larger the planet is, the bigger the planet. And by knowing both the mass and the radius, so having both curves, it's very important, we can then calculate the temperature, estimate the temperature of the planet. And this is happening at the moment only for very few planets. We can think about the HR diagram for the stars and compare the HR diagram of stars with a potential of planets. So similarly, we can plot the planets in a radius to mass diagram and distribute the different categories of planets we have found so far. And I would like to ask you if you think that this is enough to characterize a planet and understand its behavior. And of course, the main answer is that yes, to a degree, it is enough. We can separate the gaseous from the rocky planets, but while we observe more and more planetary planets and find all these different super Earth categories and some information about them, the answer is that this diagram is not really enough to understand the planet. For the stars, it was the perfect revolution, let's say, because we really understood how they evolve, how they live. But for the planets, it's not enough to know just the size and whether they are rocky or gases, because planets are much more complicated and they undergo much more complicated processes. We can have a look in our solar system, the planets in our solar system, and in order to understand better this complexity, let's say. So we have the 4 rocky planets, and by having a closer look, we will see that they're completely different. So Mercury has no atmosphere, has a very large core. Venus has an extremely hot temperature, is cloudy. The Earth has ice, has water, has a very complex and diverse climate. And the Mars is very also different because it used to have water, it doesn't have anymore. And these are only few differences between them. And one very important component is the atmosphere of the planet. So here you can see the 3 different profiles of the atmospheres of the terrestrial planets. And it's very easy to observe the difference that the Earth's atmosphere, in the Earth's atmosphere. The most important thing is the stratosphere, which is unique in our solar system. And of course, the other 2 planets don't have it. The stratosphere is also very important for life on Earth. So there are little things in the atmosphere that can show us details about geological or astrophysical processes on the planet. The same applies for planets, the gaseous planets of our solar system. So although they're all gaseous, they're completely different and they have different characteristics. So the bands, patterns that are not observable on other planets are only in Jupiter. Of course, the rings in Saturn, Neptune that doesn't have any activity. So it's something that helps us understand this complexity. So the main component and the key to better understand the planet lies within the atmosphere. There are much information that we only get from the atmosphere, and is at the moment the only window we have to better understand these planets, considering also that these planets are very far away, there is no other way to approach them, so the atmosphere is the key. For a few planets, we have managed to characterize the atmosphere. So, for example, we have found water vapor in some planets, and K218b is an example. Water seems to be a very common element out there. So the techniques we had also were focused on identifying water, and this was done successfully. WASP-76p is another example of extreme cases. So with, for some planets we have found and we have measured the difference between the temperature. So on the day side, water is getting evaporated, and on the dark side, water is condensed, and then it is practically raining iron. So because the planet is tidally locked. Then there are some planets for which we have managed to measure again how they are losing their atmospheres. So imagine that they're leaving a tail as they orbit the star, just like comets. And finally, for only one planet, which is 1897-33b, it's a very common planet, we have managed to measure the rotation of the atmosphere. And because the rotation is very high, it's very large, we know that it's that large that is almost a wind. So it's like a wind itself. And we have managed to do that with the Doppler shifting, measuring the difference. And as you see, the red and the blue, meaning that the rotation of the atmosphere is moving very, it's having very large variations. Again, the future at the moment, we know that it's bright because there are even more instruments for exoplanets and for characterizing them, but the only dedicated instrument will be ARIEL. This is where we will focus now. So ARIEL is a European Space Agency M4 mission prepared for launch in 2028. It will be a telescope of 1 meter aperture, and it will carry a spectrograph to cover between 0.5 to 7.8 microns. So mostly the infrared, but some visible also as well. The main questions that it's going to answer are what are the exoplanets made of, how they form and evolve, and finally what is the weather there. In order to achieve that, it will observe 1,000 exoplanet atmospheres. We need a large number of planets in order to answer to these questions, and that's why it's going to be the first dedicated tool as well. Now, the main goal for ARIEL will be to find out the chemical compositions of these planets, of all known planets, and finally create what we imagine as the planetary H-R diagram. So we mentioned the H-R diagram for stars. You can imagine the revolution that happened, and we really understood how stars live and evolve. So the main goal and expectation is to do the same eventually for all known planets. We'll start from the 1,000, of course. This diagram seems quite complex, but we'll try to simplify it. So above the hydrogen helium accretion limit line, which is this one, all the planets will be, the gaseous planets will be there. So all planets that are massive enough to start accreting gas, like Jupiter, for example. On the other hand, on the bottom line, which is the impact escape limit line, this one, all the planets which are not massive enough and they will not be able to accrete any gas and have atmospheres will be there. So like Mercury, or planets that have lost their atmospheres during their lives, and they will be there as well. On the right-hand side, there is the surface melting line. And this is where all planets that are lava worlds or very extremely hot and very close to their stars as well, all these planets will be placed there. In between, all the smallest rocky planets like Mars, Earth, and all the super Earths that we're finding now will be here. Super Earths that also, maybe they have atmospheres or they don't have. And finally, there is this runaway greenhouse line, the water runaway greenhouse line, where planets that have lost the water, their water will be there, like for example, Venus. And there are some smallest details, like on the bottom here, where we have planets completely made out of methane, like Titan in our solar system. and even more examples that we expect to find later on. The second main role for ARIEL will be to find out how these planets ended up to their current state, like finding out the planetary history. Now, we can start and try here to follow the path of a planet forming. You can see at the bottom we have the planetesimals, which are the small rocks which come together to create and form the planetary embryo, which is the protoplanet. And if accretion stops here, the planet will end up as Mars, for example, a very small rocky planet. If accretion continues, it will end up as a larger terrestrial planet, like the Earth, for example. However, things get more complicated for larger planets. And the mystery starts here. So planets that are massive enough to start accreting gas as well, they will continue to accrete gas. And if during their lives lose their gases, this atmosphere, they will end up as a terrestrial planet around here, like the Earth. Or if they don't lose this gas, they will end up as super Earths around here. Now, if the planet, the protoplanet, continues to accrete gas, even more gas, and is large enough to get more gases in the atmosphere, the protoplanet will be something like a Neptune. And if it loses the atmosphere, it will end up again as a super Earth or a mini Neptune. If it doesn't lose it, it will become a Neptune, like our Neptune. And finally, we have all the planets, which are gaseous planets. And if the planet is very massive and massive enough to continue accreting gas, like Jupiter, there is no way to lose the gas, so it will end up as a gaseous planet like a Jupiter. It's quite complicated, and the knowledge we have so far is very limited, and all these are based on different predictions and models. So this will be a quite big revolution for planetary science, let's say. And this is what we expect to do during the next decades. There are even some planets that, like Jupiter-type planets, that are formed quite far away, further away from their stars. But because of interaction with the protoplanetary disk, they migrate inwards. These are the hot Jupiters. With ARIEL studies, we will be able to trace their paths and find out where in the protoplanetary disk they formed and whether they interacted also with other planets. And finally, we will be able to do some planet weather studies with ARIEL. So by observing at lower or higher temperatures, we can get different structures for the planets. For example, at low temperatures, we get more complex structures like, for example, in Jupiter that we have the activity, or in high temperatures, we get patterns as like the bands, which are smoother. But this will be for fewer planets. Now we can talk about the methods that ARIEL will use, and the main method will be the transit spectroscopy. So the transit spectroscopy method is focused, as it says, on spectroscopy. What we do is we observe the planet as it orbits and passes in front of the star, and we observe it in different colors, in different wavelengths. The reason we do that is because we want to find a variation in the size of the planet, and the size is not changing, of course, because in reality it's changing, but because of the absorption from different molecules. So for example, there is here a diagram where we see in different wavelengths how the planet looks like, the size of the planet. So in 1.4 microns, the planet looks much larger compared to 0.7, let's say, microns. And this is because of the water, the presence of water. So the water is absorbing and the planet looks bigger. The atmosphere is like more opaque, that's why. So imagine the same for other molecules and also for all the different planets. The second technique is the Eclipse spectroscopy. And what we do when we observe a transit, a planet passing in front of the star, we actually observe both the star and the planet, so the star-planet system. So we wait for the planet to go behind the star in order to observe separately the spectrum of the star, and then subtract this spectrum from the combined one to get finally the spectrum, the emission spectrum from the planet. Imagine that this is very difficult, and the spectrum is around 100,000 times smaller than and fainter than the combined spectrum. However, it can still give important information about the atmospheric structure and some more difficult molecules, let's say. This is the emission spectrum of the Earth, quite nice example to understand how it looks like. And you can see here the different molecules, and also the spikes, which is carbon dioxide and ozone, very characteristic patterns in our spectrum. Ozone is very important, as we said, in the stratosphere as well. And finally, another method which will be less, let's say, used is phase spectroscopy. In that case, we observe the planet, the full orbit of the planet, and from the shape of the curve, we can better understand some weather maps and construct 2D maps, but this will be for very few planets. Practically, every science mission, in that case ARIEL, has to be well organized and get a plan, very precise plan. So the main plan is that it will observe in a glance 1,000 planets, the transits of this large number. Then in the second round, it will focus on 500 planets to get more details about their structures. And finally, around 100 planets will be observed, will be chosen based on how interesting they look like. And in this stage, we would like maybe to ask, okay, how ARIEL will do that practically, or this will be done in 2028, not now. What are we doing now? Because it's quite early. Of course, one thing is that the satellite is being prepared and designed. So very soon, the satellite will be they will start building the satellite. But the second thing from a scientific point of view is to prepare the mission, prepare the observations, as every observer plans their observations. The same with ARIEL. And imagine that there are 1,000 planets which are already known, will be already known planets. So it's very important to observe them one after the other. There will be transits. And transits are very specific phenomenon happening at a very specific time. So it is very important not to lose any transit and not to lose any space, time and space. So this is especially important for transits because we don't want to end up in situations like this, where we have missed half of the transit, and that means missed important information about the planet and the star. Very recently, 2 years ago, we conducted an observation for WASP-83b, which was an already discovered planet. And the last observation was in February 2012. So we observed this planet 2 years ago, 6 years after the discovery, and we expected an uncertainty of ±9 minutes, which doesn't seem a lot. However, we found a time shift of 25 minutes, and we did more observations to confirm that. And if we extrapolate that to the time that ARIEL will observe, ARIEL would have missed that by an hour, let's say, or at least become delayed. So you can imagine that the same can apply for all these planets if they are not followed up and just forgotten and not getting any further observations. This is actually where the small or medium-sized telescopes from the ground can become important and useful. And contribute to the bigger picture, to a large mission like ARIEL. And it's like really that it doesn't require a lot of capabilities or specific tools. So it's a small telescope with a CCD camera that can follow up these targets. This is where actually we initiated the ExoClock project, and not only to better organize this effort and prepare more efficiently the mission, but also make the best use of resources, because there are resources out there, but they need to be organized well and combined together. So the ExoClock project is a project dedicated to monitor all the ARIEL targets, the mission reference sample targets, which is continually updated because we will have new discoveries as well coming from tests. And the idea is to monitor and estimate as precisely as possible the transits to make the mission as efficient as possible. So we have created a dedicated website, which is a platform. It's a service, and it is open to anyone interested. There are 1,000 ARIEL targets. They may seem a lot, but if it is organized well, it doesn't need a lot of observations. It's one per year for every target. At the same time, every target and every transit is a unique opportunity to contribute to the mission. And of course, all these observations can be used for further research apart from ARIEL. Now, the ExoClock project has different characteristics. So one is that it's open to contributions from different communities, and this is one very important idea for us. We don't want that to be limited just to professional observatories, and that's why we have created the website, which is interactive. So it is really open to contributions from other observers, either amateurs or people that have access to telescopes. It is also an integrated platform where we integrate different data, not only the ground-based from our network, but anything that is out there. And finally, it's interactive, which means that it's a user-friendly website, platform, and I will show you some characteristics later. As we said, the main scope is to refine and monitor the ephemerides of all the targets to increase the mission efficiency. Meaning having an integrated platform is very important to make the best use of resources. So there will be space data are already there, coming from CHEOPS, for example, or other space instruments for targets that are not easy to observe from the ground or that they have rare transits. There are also literature data in our platform. We try to make use of all available data, for example, from past or future publications. And finally, it is very important to empower the international and more like a collaborative spirit. So we also have synergy with all other ground networks that are observing exoplanets and transiting exoplanets, but for other purposes. Now, we have created an exoplanet characterization catalog, which includes all the important information about the targets. This is quite important because we want to achieve and maintain consistency in the project. And it's very important, especially if we are preparing for a space mission. At the moment, this catalog includes all the targets of the mission reference sample, but it's continually updated based on the new discoveries. So you can visit that as well, and you can see all the details currently updated and known for these planets. And we try also to correct the mistakes that are in different databases. As I said, it's an interactive platform, so any observer that is registering in the platform is getting a personalized scheduler based on their telescope, their location, their sight horizon, and based also on the catalog that we have created. So by registering a telescope, you will get to know which target exactly to observe and when, without having any limitations. And second important element is the target prioritization system. We have created this system in order to distribute the different targets more efficiently. So all the targets that we will see and will be suggested to observe will be flagged with different priorities, with low, medium, or high priority. So they're flagged based on how rare the transit is or how big and large the uncertainty is. So you know which target to observe rather than another. After having observed a transit, then you analyze it, or the observer analyzes it, and then you upload it in the website on the platform, where if the planet transit is okay, is like fine without any mistakes, it is directly modeled on the platform for consistency reasons and then published by our team on the website. If it needs some corrections, we will send it back to the observer for some further feedback. Then they will upload it again, and the same happens again, like it's modeled on the platform and published furthermore. In a few words, ExoClock is open to everyone, as I said, and we have currently also amateur and professional astronomers, and even some students at some point. It is a platform that offers a live up-to-date ephemerid service for ARIEL at the moment, but these targets maybe are observed for other reasons as well. And the role it has is a service, a very important service for the mission, but at the same time, more in an educational outreach perspective, because we want to combine and bring together different communities. And this is where actually things become better, because different audiences have different backgrounds, very important for a mission. All observers become co-authors in publications, and of course on the website they get acknowledged. And they get feedback, as I said before, their personalized schedule, and we try to connect everyone with each other by having some webinars, some monthly newsletters, in order to make this effort more educational as well. We have now 1 year in operation. We launched during in the European Planetary Science Congress last year. We have more than 160 participants, out of most are amateurs, as you see. And they have registered more than 200 telescopes coming from different countries. And one very important element in our project is that there is no commission or limitation. Observers can have only one transit and they can leave, or they can start an observation and then come back, return to observing more planets. And this is very important because someone, for example, has time one night but is not really interested another night for the specific reason or whatever. The distribution of the planets we have, the telescopes we have so far, they range between 7 to 40 inches, as you see. So mostly small to medium-sized telescopes. And the observations are 1,100. The number is increasing every day. 172 targets out of the 370 in total have been observed in the system. And this is continually updated, as I said. The latest update is that 25 planets are updated, the ephemeris of these planets. And this will be shared also with other communities for other purposes. And this is all about the ExoClock part. So at the same time, we really wanted to create some tools and open exoplanet research to more observers, to more people that are interested, but they don't have probably either the background, the tools, or the capabilities. So the reason, for this reason, we created the Exoworlds Spies project, which is a separate platform. It's the educational place where we share all the material for observing, analyzing data, updates on that, and also all the science behind transits. So in the website, you will have and you will find observing strategies on how to observe, data analysis software, which is a dedicated software we have created in order to facilitate all users, and different material, videos, data for training, and of course, observers can ask any question they have anytime. I want to share again and mention that because in science, it's very important to have collaboration. We really believe that science should be open to everyone interested. And for this reason, we have created all this material to enable this process. And by having different communities and different backgrounds, we can make the process more, let's say, rich. So eventually have better results as well. So we have three pillars, let's say, the research part, but also education, which is a continuous process, and also outreach in case someone just wants to know and learn the news about something. In the website, you will find different sections, and one is how to observe, which is the first step. You will find the targets, the way to plan the observation. This is connected also to ExoClock if you are registered, but you don't need to register if you just want to have a look. And also how to set up your telescope. So all the little details that can make a difference to have a successful observation. And I would like to mention that we have observers that didn't know anything at all, and by just studying the material there, managed to have their first observation successful. So it's something that can be done. The second part is how to analyze, and there is a separate dedicated section on the website, which is with the software. So we have created the Holomon photometric software, which is the tool that we use for analyzing the transits. And this is a very user-friendly tool, but at the same time, it is very efficient and professional, let's say. So this is what we use in our research and used by other communities as well. It is open, free, and it looks like this. The final result, as you see on the right side, is the final light curve modeled as well. And you can have the main information, the main details about the planet. Now, the main characteristics for HOPS are that is open source code, so it's open to contribution from different communities. It has a generally user interface for all operational systems, so there is no need for scientific or coding background. It works with Windows, which is quite important. It is written in Python, so that means it's easy to implement different patterns and new all the time updates. And finally, it's flexible on all data formats, so it is generally suitable for all small and medium-sized telescopes. Now, we have also in the website, a database where we have shared different observations for different targets. So this is mostly important for someone that doesn't have equipment or has equipment and would like to get trained or see how it looks like to analyze a transit and what the result will be. So 26 available observations for different targets, and these are kindly provided by our ground networks and also some collaborators for training purposes. So even if you have a telescope and you're not sure if you want to observe a transit or if you like it, you can give it a chance from this database, download also the software, and do the analysis yourself and play around with the data. So coming towards the end, I would like to invite everyone or anyone that is interested to ExoClock, and under this collaborative spirit, every transit counts and is useful. Small telescopes are useful and can become important for a large mission. And that is why we started this process from quite early to make the best use of resources. If you're interested and you also have telescope and the equipment, you can start directly at ExoClock, register your equipment and start seeing around how it looks like. If you don't have equipment or you're not sure, you can start training at Exoworlds Spies with all this material I've shown. And if you're not interested at all, you can still register to the monthly newsletters to get the updates about the mission and the planning of the mission. And I would like to thank you very much for your attention and take any questions you might have.
Anastasia, thank you very much indeed. That was really very interesting. And again, guys, we'll make sure that the links go up on the forum, so you can, if you wish, follow up on that. I think I'm certainly going to follow up on that. Grant, perhaps that could be something, another community project that we could kick off on the forum.
Absolutely, it looks really interesting.
Yes, indeed. Yes, indeed. Okay, so there are some questions come in. So the first one is actually to Helen. Helen, if you're there, feel free to unmute yourself.
Oh, that's my fault.
Oh,
Sorry.
there we go.
There we go. You should be okay now, Helen.
I'm okay. Hi there. Hi, Anastasia. Thank you. My question, why haven't we found so many super Earths? Or why have we found so many super Earths when we haven't got any in our own solar system? Why do you think we haven't got any?
I think this is the main question that is not answered yet, and actually we don't really know why this happens. It's a big mystery, and that is why we initiate more dedicated, let's say, instruments and surveys, because we really want to know what is happening with these planets. Like, okay, are they just bigger than the Earth? They have lost their atmospheres. It's a big mystery at the moment, so I don't think there is an answer, and it's going to be probably answered quite like in the future. I don't think it's going to be answered very soon.
Great, thank you. It's great when we don't know things and we go off to find things.
Yeah, absolutely, Helen. Yes, indeed. Yeah, good question. Good question.
Can Leo ask a question, Daz?
Yeah, of course you can.
Okay. Are there any stars without planets? With no planets?
Yes, there are. I mean, okay, most of the planets we know, most of the stars we know that they have planets. Okay, of course, the most important thing is to observe the star as much as possible in order to conclude to this result. At the same time, it's very hard to say if a star doesn't have a planet at all, because it really depends also on the angle that we observe. So not observing a planet around a star doesn't mean that it's not there, because we are observing it from the Earth from a specific angle, so we might be limited, and that's why we don't observe any planets around them. But definitely any stars, for example, like neutron stars or stars that are beyond their life, these will not have any planets.
So you would only know if you could observe them from every angle on every point of that planet year?
To be absolutely sure, yes. Or if we combine different methods like the radial velocity and the transit, and then we know that there is nothing there. There were many stars that we have not found planets with the Kepler telescope, for example. But saying that they don't have planets is very hard.
Thank you.
Cool. Good questions, Leo. Yes. No prompting from Dad at all. That's all right. That's good. Okay, back to the chat board. I think it's Terry McKay. If you're there, Terry, you want to ask your question? No mic attached. Okay, no worries. So Terry says, is water seen in great concentration on the so far observed exoplanets?
Yes, but still it's very hard to say what concentration, because as I said, our current, I don't know, maybe I didn't mention it, but our current instruments are also mostly focused on water. So we can't say the proportions with really like big certainty. So even for the case I showed you earlier, it's not really sure how much water there is there and the proportions with other molecules. So in order to know more precision, we will need further instruments. For example, as ARIEL will do in the third stage or the second stage, where it will observe in more detail some planets. So the current instruments are mainly, for example, Hubble, which was not designed to do this job, and it's quite limiting.
Okay, great, thank you. Terry, I hope that answers that for you. Jack says, is Ariel, oh, sorry, Jack, if you've got a microphone, if you want to ask your question. Okay, I'm not hearing anything, so I'll go ahead and ask Jack's question for him then. So he says, is ARIEL spectrograph sensitive enough to detect chlorophyll, an indicator of life?
Interesting. I don't think so. So ARIEL will be more sensitive to all the different molecules that we know, as like methane, all this that we are more familiar with. But for an indicator, we will need other instruments, let's say, not spectrographs only, but kind of a combination of telescopes to observe in more detail the spectrum of a planet and identify this chlorophyll, or we can't really know. It's mainly for molecules. So the closest one, let's say, will be kind of methane or ozone or oxygen, but oxygen is very hard. So it has a very faint spectrum. It's very hard to observe it. So indicators for life will be very hard with ARIEL. That is why it has different codes. This is something we can clarify in general. Mm-hmm. But still, there is an astrobiology team in the mission that will try to extract some information if possible. But in general, no.
Okay. Okay, great. Thank you very much. Thanks, Jack. Thanks for the question. I think we're at Simon next. I know you've got a microphone. I can see that on you.
Yeah, thanks, Des. Yeah, hi, Anastasia. Thank you very much for a very interesting talk. I think my question really leads on from the previous one, really, where you've explained about molecules on spectra. I was wondering along the lines of if it would be possible in the future to take the emission spectra possibly from planetary atmosphere and see if there's any indication of industrial pollution, sort of CFCs, that sort of molecule, and maybe even light pollution from street lights.
I think in order to reach that level, we will need to have a big number of observations, and that's why the third stage as well will be for more interesting planets to observe any variability, for example, in their spectra, and small details that can show us things that we were not expecting. The most important thing is to have a lot of observations. So yes, at some point in the future, ARIEL will do the first big survey. We hope there will be more. Yes, the main thing is having a lot of observations and continuous observations to get more details about it. Having or observe something that is not really familiar to our current knowledge, and then do follow-up observations to identify what is causing that.
Great, thank you.
Thanks, Simon. Thanks, Simon. Yes, one day that could be interesting. There's street light pollution on another planet. We're not the only ones suffering from that. That would be okay. So that's the end of the questions that have come in by the chat. So unless anybody's got any others. So again, we'll certainly put the links up on the forum, Anastasia, to the resources that you've been talking about, so people can register. And again, I think we'll look to get something set up on the forum so that we can get another community project running. Our starting one on variable stars from a talk we had a few weeks ago. So I think this will complement that quite nicely. Lots of people saying thank you very much for a very interesting talk. Again, there's no other questions come in. So Anastasia, thank you very much for your time. Really, really interesting talk, and we look forward to perhaps future updates from you.
I was going to say, hopefully we can have you back in a few years and see how it's going.
Yeah.
Quite early, so we still have a lot of time. And anytime you would like to ask any question, you can drop me an email. I'm the coordinator, so I will check any emails that you will send. And many thanks again for the invitation. If you would need some help with the form that you will initiate, I will be happy to assist.
That's super. Thanks very much,
That's
Anastasia.
great. Thank you very much
Just
indeed.
before we disappear, just to mention that our talk next week is Stefan from Nina, who's going to come and give us an introduction to the Nina software. So that's next Sunday.
Indeed. Great stuff. Anastasia, again, thank you very much indeed. Grant, thanks very much for the technical stuff. Everyone, thank you for your questions.
Thank you all.
Have a great week, and we'll see you all very
See you
soon.
next Sunday. Thank you very much.
Thank you all.
Bye.
Bye.